So in this lecture, in the next lecture, we'll talk about a resource semantics. We're working our way up to that. And I'll start by kind of explaining what I actually mean by that. So when people use the word semantics, it has many different meanings. So there's operational semantics, where you describe how a program runs, and we've had examples of that. But the traditional meaning of the word semantics is that you take the syntax of the thing that you're dealing with, like linear logic, and you interpret it into a mathematical domain. You say, okay, in performing this linear logic, I interpret it as some kind of Hilbert space or something like this. Okay. So the problem with that is that I've been extremely careful throughout that to be constructive in all that I do. When the traditional types of semantics is done by interpreting the mathematics, usually you give up on this constructive nature on your investigation. You say, okay, well now we're looking at the intuitionistic case or the linear case, but we're looking at it with classical means. In other words, we use classical logic the way mathematicians would be. And as an intuitionist, this goes against my grain. Okay, so I don't want to do that. So what I want to do is I want to give a semantics, but I want to do it entirely constructively. Okay, so I want to give a constructive interpretation of linear logic in terms of the resources that are being used, and I want to stay within constructive logic. Okay. So what does that actually come down to? So somehow what we want to get rid of the linearity in some sense, but we want to keep the intuitionistic nature of what we're dealing with. So that's my objective. Okay. So the intuitionistic being constructive in the sense that whenever you give a proof, you have a witness and you can actually reduce things like we did in the case of concurrent semantics. Okay. So if I wanted to be a little bit more precise than saying resource semantics, okay, I would say constructive resource semantics. Okay, and this will take us more than one lecture, okay, but I think hopefully we can get reasonably far today. Okay. So the main thing is to get rid of this part of linear logic that is actually that the resource that your assumptions are resources that are consumed during a proof. Because if you're just doing intuitionistic mathematics, that's an unfamiliar thing. We introduce that specifically due to linear logic, but how can we eliminate it? Okay. And the way we eliminate it actually is in form of, we move the stuff into equational reasoning, which may be a surprising thing. So the idea is that somehow the linearity, the substructural nature of the logic is mapped to equational reasoning. Okay, so let's see if we pursue this. Okay, so what I'm going to do is, we'll just do the purely linear case to begin with as usual, so we can focus on the essential thing. So if we have in linear logic a sequent from delta, I can prove A. Okay, and delta might be something like A1 through AN. Okay. What I'm going to do is I'm going to say these things are resources, and I'm going to label each of them uniquely. And that label is going to be a way to refer to the resource. Okay. So we already label things as variables, x1 through xn. So what I'm doing here is different than that. I'm not using the variables, but I'm using a different kind of labeling. So I'm going to translate this over here into something like A1 at alpha 1, AN at alpha n, and then from that I prove A at P, okay? And so these are variables. So let's call these resource variables. And this over here is a resource expression. Okay. And what I want to say, if I have these things, if I have resources alpha 1 through alpha n, I can prove A using the resources in P. And in order to be able to write down P, I need to be able to say, what is the P? Well, a resource expression is either an alpha, okay, so I can use a variable here, or it's a combination of two resources. Okay, so I can combine two resources and get another one, okay? And there's a third possibility, that is the empty resource, and I'll write this as epsilon. Okay. So, so typically, for a sequence to be the translation of a linear one, this P here would look like alpha 1 star alpha n. Okay. Okay. And if n equals 0, that would be epsilon, right? Because you multiply 0 things, you get the unit, which is a multiplicative unit of the star, and you get epsilon. So we have some laws here that say something like this. So epsilon times p equals p combined with epsilon is p. Because epsilon is the empty resource, that means nothing in the context. And so adding that to a resource expression p, this gives you back the same p. Okay. Now, other equations, what other equations might we have about these resources? If we think about this sequence representing in this resource form. Commutativity, okay. And that's because the order of these assumptions here in linear logic does not matter. So we can flip these two. So we also have P star Q equals Q star P. What else would we have? Yeah?
P star Q and Q star R in bracket.
Yeah? It's associative, and that's because when you put these things in the context also is stable under associativity. Okay. All right, so I think this is all that we have so far. Because what do we assume about the context is that the order of the assumption doesn't matter. Okay. And that the way we assemble it from left to right to left doesn't matter. Okay. And that the empty resource is kind of a unit of this multiplication because we start with empty, we add something, then it's the only thing we have. Now you can, yeah?
So in order logic probably wouldn't be commutative.
Okay, the word that's on the top of my tongue, and the tip of my tongue when you asked the question was in ordered logic, okay? We'd have another resource combinator here, okay, which would have an epsilon. And it would be associative because even in the ordered context is associative, but it wouldn't be commutative.
So is there any logic in which you consider associative?
Yes, there is non-associative logic. Okay. And in non-associative logic, we don't consider associativity. But there is some debate whether this is actually useful logic. So the basic issue is that in order to recover the full power of intuitionistic or classical logic, you need some kind of modalities. And traditionally, it has been difficult for non-associative logic to define the right modalities. Okay. So it's with order, it's borderline. Okay. We can find this mobility which makes things mobile. But how do you restore associativity in the non-associative logic? Because it's associated with more than one thing. Okay. So it seems to be hard to do. So one can define that, and people have thought about it, I think, to some extent in computational linguistics. But I'm not sure how successful it is. Okay. Okay, so this seems like a nice step. Okay. And we'll see if this actually bothers something. If by doing this we can actually get rid of the linearity here, the substructural nature, and encode it entirely within this kind of equation of reasoning on these kind of world expressions. Okay. So we have to define them rules. Okay. And there's different ways of doing this. And we'll see another way next time. I don't think I'll get around to this today. My goal for today is do it in such a way that proofs here, okay, are in bijective correspondence with the proofs over here. Okay. So this is a very strong requirement. You very rarely get this in this kind of semantics. Okay. And you will see that the system is a bit odd. Okay. And we look at these corners of the system that you define that way, and then the next lecture we'll make a resource semantics where you no longer have a bijection. And in fact, you might say that the system over here has some advantages over the original system. But for today, I really want to get a full bijection. So let's start. What is the initial rule, or the identity rule? What does the identity rule look like? Okay. All right. what would be the cut rule? I'm going to write gamma because I'm going to reserve delta for these things, and I'm going to call these things here gamma. So if gamma proves P, okay. Okay, R. Something like this. Okay, any thoughts on this, on these two rules?
Could we write it as R star alpha and just write R star P in the bottom?
Okay, so there's a kind of a trick that we sometimes use. We say this is a proof of CR that can use alpha. And then instead of doing the substitution, then we say R star P. Okay, when we do that, actually, we potentially change the meaning of this in the general case. Okay, so in this particular case, I'm trying to maintain some invariant that each alpha occurs exactly once, or at most once in the P. And if it occurs at most once, then you can isolate it and you can replace it by P. If it may occur multiple times, then there would be a problem because alpha would be left here. Okay, so this is okay. Okay, assuming uniqueness of alphas in any process expression P.
What if we have width or
Right, so we have to get through all the other rules to see what it, yeah. Okay, so this is actually not quite the rules that I want, okay? And maybe after we go through a few rules, we'll see why that's the case, okay? Okay, so let's do some logical connectives. So let's do implication, okay? Okay, the parentheses, of course, are always like this, right? Because it annotates the whole judgment. So if from gamma I can prove A implies B, how can I prove from gamma A implies B with resources P? So I want to preserve that general form of the invariant over there, mimicking the rule that I have in the linear case. So how would I do that? Yeah?
Under the contact gamma, A at alpha can prove B is the expression P and
Okay. And the important thing here is that, right, alpha has to be fresh, right? You have to pick a new alpha to make sure that you don't violate the invariant, that all these things are distinct, right? All these alpha 1 through alpha n all have to be different. And so we have to pick a new alpha over there, okay? All right. So let's see what happens to the left row. So we have gamma, and we have A implies B at alpha. And we're trying to prove C, okay? Okay, how do I do this? Well, there's always certain things that we know that we don't have to think much about, right? So let's write those things down. So there's going to be two subproofs, right? Okay, so if a turnstile here and a turnstile here. What's going to be the conclusion of the second one here? C at some resources. Let's keep that open for the moment. Okay. What's the conclusion here? A at some resources. Here we have an additional assumption, which is B at some resources. Okay. Pretty soon we'll have to start to think, actually. Okay. No, this is just the single-step inference rule. We're not doing focusing yet. Okay, so we're just writing on the implication left rule. Oh, yeah. Yeah?
We also need to split gamma into gamma by gamma.
Okay, so now the reason I don't want to do that is because if we do that, then we just rewrite all the rules of linear logic, and all the resource stuff is all redundant, right? So if you split the context, right, we have this thing that I wanted to get rid of, namely the linearity, that each assumption is used exactly once. So I want the assumptions to be monotonic. So this is a very important thing. So over in this system here, I want the assumption, the antecedents, once you have an assumption, you never eliminate it. Okay, so the complete opposite of linearity. But what you're totally used to in mathematics, once you make an assumption, you have it for the rest of the proof, right? I mean, that's the whole point. And that's also true in intuitionistic logic, in ordinary intuitionistic logic, but false in linear logic.
For the identity rule, doing it again.
That's right. So because of that, because we never get rid of assumptions, it's going to be left here. So there's going to be some assumptions left. And now you might think, is that even sound? Because in the linear case, right, we're required to use exactly one assumption, A, to prove A. So why is this actually sound?
Because it's going to be reused later for some other goal.
It's required the P to like match up with all the assumptions.
Right. The later has to do with resource management, but the argument here is that what you have over here is alpha. And so that means that among all the assumptions, you can only use the ones that have label alpha and nothing else. Okay. So we allowed other stuff, but it doesn't invalidate, okay, because we say explicitly which ones are allowed to be used. Okay. So let's go back and change cut in the same way, in the same spirit, which I should say. So because we never want to get rid of an assumption once we've made it, okay, because we want it to be monotonic, we'll just have gamma, and we move that to both sides, okay. Do we need to change anything else?
We need to say that E and R are disjoint.
Right. So we need to somehow say that this alpha is new up here, right? Okay. We don't want alpha to be already in the context and reuse it. So there's some restriction on alpha being new in this up here, okay, if you read it bottom up. So we prove A at P, then we assume a new alpha, okay, which has a local scope up here, and then this is our conclusion, okay? And so that's our cut rule, at least one of our cut rules. Here we already say alpha is new, okay, so this one should be okay. Okay, so now we come back to here. So now we know a little bit more because we're going to put gamma over here. And we're going to put gamma over here. Okay. Now the other thing we're going to do is, because everything is monotonic, even though we apply the left rule to this, we're going to carry it over. Okay, because we never want to forget any assumptions that we have. So we're going to have A arrow B at alpha here, and we're going to have it in here, A arrow B at alpha. Okay? Okay, so the rule is starting to take shape. Okay. Now we have to finish it up somehow. Okay, so we have like 1, 2, 3 spots, and we have to reconsider this maybe. Okay.
A at.
Okay, A is going to be at some P. Okay, good.
Now that has to be removed from things that can be used.
Okay. So we have P star. Okay. What else has to be removed from the things that we can use? Alpha, right? Because we're using this assumption It's supposed to be linear, so we can use this assumption only once. So we're using the same trick we're using kind of here. Right? So in order to use it, we have to remove that from the things that we can use here. Okay? All right, what about this assumption here for B? That one has to be used in this proof, so how do we encode that? Yeah, we have to have a fresh, call it beta, make up a new beta, and beta is allowed to appear over here somewhere, right? What else is allowed to be used in this proof? Certainly not alpha anymore, right? We got rid of that. What about P? No, because that's used over here. And so what's left? Whatever is in the gamma, where is that? How do we get our hand? R. Or Q. Okay. I'm sure that the alphabet here is a little bit suboptimally used, but okay. So we have an assumption A or B at alpha, and we're allowed to use that because it's over here. So it's not something that we have gotten rid of, so we can use that. We can apply the left rule. And then we have to prove A with some subset of the resources, P, so that has to be allowed. All the resources that occur here have to be allowed. Then we create a new resource beta, which we're allowed to use in this subproof. And all the resources that's not alpha, not P, are also allowed to be used here. Okay, so we put Q over here. Okay, does that make sense? Yeah?
I think in somewhere we need to put the restriction that, for example, in this rule that P and Q, the variables in P and Q are disjoint.
That's right, because we don't have any repeated variables in here, because there are no repeated variables.
Yeah, but where should we put that restriction?
Okay, right here.
For example, for the cut rule, we didn't say that the R and P have disjoint variables.
Right. So, yeah, we should say that. So there's a global assumption whenever we form one of these things that there are no variables that are shared between the two sides. Right. Right. Okay. So now the question is it really sound, right? Is it okay to keep this alpha here and, just continue on, right? So how come we can leave this assumption here? Well, the intuition is because this is the only occurrence of alpha. So that means we remove it, so alpha is not here. If something isn't on the right-hand side, we can't actually ever use it, right? So in the end, what we want to prove is a strengthening theorem. Okay. So let me put that over here. Okay. Strengthening. So if from gamma we can and A at alpha, we can prove C at R, and alpha is not in R. Okay, so it's not a component of that product. Okay. Then we can prove it from gamma alone. Okay? And we'll have to make sure as we write down all our other rules that this continues to be the case, right? If a resource is not mentioned over here and it occurs on the left, then we can't actually use it. So we can actually do that, right? And it's a little bit stronger than just saying we can prove this, but exactly the same proof will work. Okay, we don't have to change our proof simply because we can't use this assumption. So we'll have to be careful that we can't use that assumption. Okay. Okay. All right. I guess I'll do it over here. Okay. Let's do tensor. Tensor right rule. Okay. Any bids for the tensor right rule? Yeah. So how's it going to look? Okay, we keep gamma. Okay. Yeah?
P star Q.
Okay, makes sense. Right. This is easier somehow than the left rule because the right-hand side is not identified by a particular resource alpha. So that little trick over there that by removing alpha, we didn't have to do that, right? If we didn't have to do the alpha-beta trick here, this is very similar. It says we have P star Q, P goes here, Q goes here. And then in addition, we have to remove alpha and add beta. Okay. And we don't have to do that with the tensor. All right, tensor left. Okay, how do we do that?
P star alpha.
Okay.
Gamma, A is beta 1, B is beta 2, U, C, and P top star beta 1,
Okay, almost, not quite.
You're not allowed to throw away our attention B.
Excellent. The rule has to be monotonic, so we still have a tensor B at alpha in here. Okay. Okay, but we can't use it anymore really because we have that, right? So we have to be a little bit careful. So for example, if you say, oh, we have this great embedding now, we can use, let's introduce a universal quantifier for these alphas, okay, as a new constructor for a proposition for all alpha p. Then, if you have something here that is supposed to be at for all alpha with p, then you could instantiate that alpha with this one here, okay, that was supposed to be forgotten. It can be resurrected from the dead, okay. So one has to be extremely careful with these kind of labeled formulations to make sure that the strengthening proper really holds, that these things actually cannot be used anymore. If you have too many logical constructs in this language, okay, then this kind of property fails. So we have to be really careful about that. Okay. Let's do 1, the unit. Right rule for unit.
So what is actually the reason why it has to be monotonic?
It's monotonic because it's supposed to be an intuitionistic resource semantics. So that means that the assumption that you make once is going to continue to be available. And we'll just track what we can actually use in a different way from before by using equation of reasoning instead of splitting the resources. Okay, so let's do the 1 as the last multiplicative. What's the right rule for 1? Yeah, add epsilon. Okay. Proving 1 uses exactly no resources. Okay. And the left rule. Okay? Okay, so the weird thing is it doesn't go away, right? Everything's monotonic, so the 1 stays. But it can no longer be used because we get rid of the star alpha here, and so there's no alpha up here, so we'll eliminate that as part of the rule. Okay. Okay, so before we get to the additives in the exponential, maybe we can write down somewhere the theorem that we expect to hold at the end. Okay, so how do we build the relationship between the two kind of proofs? So there's two translations, right? There should be 2 parts. So one is from a linear sequent and the other one should be goes back to the linear sequent. So from a linear sequent, what do we expect to hold? Yeah?
A can be proved and, for example, if all the resources in delta is labeled as alpha 1 to alpha n.
Okay, let's delta at alpha, okay. Oops, delta.
A can be proved with the resource expression alpha 1 star.
Okay. Okay, so if we label each of the resources with a distinct new variable here, alpha 1 through alpha n, then we can prove the product over here. So how would we prove that? Okay, so let's take this rule here. Okay, tensor left rule. So the last thing applied here was, yeah?
Why do you generalize the statement? Because you don't have to use all the alphas in the filter.
Okay. So how do we generalize it?
You just need to, the things appearing in the product on the right.
Yeah.
offset from the ones appearing.
So you allowed some other gamma here, like this?
Yeah, I think you use.
Hmm? Okay. Okay, so let's look at this one here. In the linear case, we have the tensor left rule applied over here. And then we just have to check that we can apply the induction hypothesis to translate the premises. Okay. Okay. Okay, so what happens? So the linear rule is something like this. Delta A tensor B proves C because delta comma A comma B proves C. Okay. So by induction hypothesis, we should be able to prove this thing here. Okay. So we'll take some slack here and put it into here if we want. Okay, so we can prove that. And then we can reapply the rule now on this side over here to get this conclusion. Okay. And if this P is essentially alpha 1 through alpha n's, adding the one alpha here should exactly make things work out. Okay. And let's see, I wanted to say something else about this. So if you have a weakening principle for this, I don't think we need to state the gamma. Yeah. We just say we can always apply weakening because with other assumptions, yeah?
I'm about to ask which approach is easier. Like, the first approach is to prove weakening,
Yeah.
and the second approach is to generalize the theorem one.
Okay.
So,
Okay, my preference would be to put it without the gamma and just prove assume or prove weakening, right? Because all the rules of monotonic assumptions never go away. We just need to verify that they're allowed to be left over at the end, basically. And they are, okay, because here anything can be collected in gamma. Okay, now for the other direction, what did we prove? So this is the soundness, which is the hard part to prove, right? Because if we were not careful, and this kind of assumption that's being left over could be used at some point, then it would not be sound with respect to the linear case. Yeah?
We need to keep those assumptions that occur in P.
Right. So we take gamma and we restrict it to P and use that to prove A at P. Prove A, right? Sorry, like that. Okay. So we need to just have defined this restriction operator. Okay. So do I need to define this? It's pretty obvious, right? These are just the things that are the alphas that I mentioned, and here we keep from gamma, and then we can construct that proof over there. Okay. Let's just check a case, like here, for example. Okay. We need to show that in the linear case, we can prove A from A. Okay. And we need the assumption that there is no occurrence of alpha and gamma, right? That every variable, every assumption has a distinct alpha, so that all of gamma gets erased as part of this, right? So that invariant we need. So it's very important that in one of these sequences, there is no assumption labeled more than once with the same alpha, or the soundness would fail. Okay. Let's see. Here, okay, in this one here, we would have to show that, so the induction hypothesis here would tell us that gamma restricted to P would prove A. That can't include alpha because there's only one occurrence of alpha here that gets removed. There's no occurrence of alpha here, so this would be gamma restricted to Q, and B can prove C. And then the conclusion is exactly that the combination of these two things, which are disjoint because P and Q are disjoint, and A or B proves C. Okay. So the proof actually works out very naturally with this kind of statement. Okay, so now let's look at the let's look at the additives just to see what's happening there, and then the exponentials. Okay, gamma proves A with B at P. How do we prove that? Well, it's pretty easy, right? Gamma proves A at, gamma proves B at. Okay. How does the additive work? Yeah? It's just the P on both sides, right? Okay. All right. So the left rule, if we have gamma, we have A with B at alpha, and we're trying to prove C at P star alpha. Okay. So you can think of different ways of doing this. The way I want to do it is one that preserves the bijection, which the proofs we already have. So how would we do that? Yeah? We always have everything already, okay? And beta must be new, right? Pretty simple. We just have to make sure that the alpha gets removed, but we keep the formula here. We add beta, and now we can use that. Okay. Okay, so additives are pretty simple. Yeah, you have a?
I'm just wondering whether you were talking about, like, you can put both of A and B in the context, but still put only one beta.
Okay. Okay, this is a tempting rule.
No, not but,
No?
but it's not monotonic, and also.
Okay, so first we have to keep A with B at alpha, and you want to call these betas?
Beta 1 only beta 1.
So here only beta 1.
So I'm just wondering whether, because you said that it seems that there are multiple choice in order to formulate this.
Yeah.
And I'm wondering whether that's the other possibility you are talking about.
Right, so this is one other possibility. This is a little odd because you introduce something that you're definitely not going to use. That's the only difference between the two.
I know.
Yeah.
You don't have access to it.
Right.
I would say that this is bad for bijection because it's different from the linear system.
Actually, I think this still works with the bijection because you couldn't use this assumption. It just seems a little redundant to do that. But another thing you could do is just call this beta, and then you have beta here. and you have beta here, okay? Except now we have two assumptions labeled with beta, and we'd have to decide what that means, okay? Okay, if you want to allow that, okay? So if we wanted to allow that, okay, then we would have to somehow say there is some projection which we can prove our conclusion with, okay? So when we project this onto beta, we have to actually pick. We have to pick this one or we have to pick that one, okay? So I'm a little worried that bijection will get lost in this, okay, of proofs. And I'm also a little worried whether this is sound, the way we wrote it here, okay? But it seems plausible that we could make it sound, right? Because when you do the projection with the beta here, even though you have multiple betas, you have to pick exactly one. So you have to pick this one, in which case this was the and left 1 rule. If you pick this one, then it should have been the and left 2 rule. So it seems like it might be okay. So if we do that, this kind of rule would actually be invertible, right? Because we can always do that, right? Break it into the components, and there shouldn't be any reason not to do that, okay? Okay, so we'll come back to that next time. I'm not going to give you the answer now. But it's a possibility. But the obvious thing to do that isn't where the proofs bijection are being preserved is this one over here. Okay.
What would the bijection even say in this case? That every such proof,
Right, so
well, obviously, if there were two ways how to prove it, like let's say A and those would be the same, like A with A, right?
yeah,
Now, you could just either do that or that.
right.
Would that be different?
We have the same choice in the original one. No, what would be different is the problem is if there's now a multiplicative and the proof gets split into two pieces, then on the one side you could pick this one, and the other side you can pick this one. And that could either be unsound and certainly would violate bijection because you would have had to postpone breaking it up into pieces until the two branches, okay? So let's come back to that next time because we'll get into a system which is more like this one rather than the one that we're doing today, okay? So let's do the exponentials because they also show up something interesting, okay? So what is the right rule for bang A? Okay, well, we'll write the things that we know already, right?
Should be epsilon for the linear resources.
And here?
Epsilon.
Okay. Actually, I was probably jumping the gun. The first thing we should have figured out is how do we change our representation of the sequent, right? Because in the linear sequent, we have two things on the left-hand side, right? Right, there's the gamma here. So how do we translate the gamma into the statement over here? Yeah?
Just put the gamma there. Just add the gamma to the.
Yeah, so I don't want to do that because I want all my assumptions to be labeled with resources, right? The resources are required for it. I don't want to have assumptions that are labeled and others that are not labeled. I want to give uniformly a resource semantics. So if I have an assumption here, what kind of resource would I ascribe to that? It's persistent, right? But what kind of resource does it correspond to? So somehow the distinction between linear persistent has to map to a distinction on the resources over here. So what would I say? How could I say that? Do you have an idea?
I mean, you could label the resources with a bang. Like the labels have a bang.
I could do that, but actually there's a simpler way to do that. Yeah. Okay. So what is the meaning of validity? When is the assumptions here say A is valid, right? That's what things in gamma say. What does A valid mean in linear logic? How do we define that judgmentally?
Without any linear assumption.
True without any linear assumptions, or true without any resources. Okay. How do we represent truth without resources? Epsilon. So why don't we just take all the things in gamma and just label them with epsilon? Okay. Well, then we have to change our mind now because we're doing something more complicated, right? So the things that are valid means that they're true without using any resources, and therefore they're labeled with epsilon. The things that are linear correspond to resources that can be consumed, so they're labeled with distinct resources, so we can refer to them. So the interesting thing is that if we take all the resources here and we multiply them into the right-hand side doesn't change. Which basically said that the resources in gammas we can always use. There's no restriction, right? Because we don't actually require this to be here. So the gamma before, in the linear case, is propagated to all assumptions, okay, monotonically. This happens automatically here. Plus, we can, essentially, we want to arrange that we can use them at any point in time because it doesn't require any resource in order to use that, okay. No resource over here required, okay. Okay, so in view of that, let's see if this makes sense. So this says we have to prove this without using any resources. Okay. Now anything in gamma that's labeled with epsilon will be carried through. Okay. And we can still use the epsilon things. It's just we can't use anything that was labeled with an alpha because those things are not explicitly mentioned over here, so we shouldn't be able to use them. Okay. Okay, so let's see if we can do the left rule and the copy rule. Okay, so what's the bang left rule? Okay, gamma bang A at alpha. Okay, proving C at, here we still prove C at something, okay. Gamma is still there, bang A at alpha is still there, okay. And we just have to fill in the holes. What other formula do we have here? A at epsilon, okay. What about the right-hand side? Yeah, alpha can no longer be used because the bang left rule, this assumption disappears. So we have P star alpha, and what do we have here? Just P, and you can think of it as P star epsilon, but that's the same as P, okay, by equation. So I should have emphasized this before. Whenever we write these rules, all the rules are interpreted modulo all of these equations, right? We don't explicitly write, you know, C at Q, and then here Q equals P star alpha, but we just assume that we can reason equationally with the resources at any point in time. That just corresponds to the fact when we presented linear logic, we didn't explicitly have a rule of exchange, for example, for the context. We just say you reorder it as needed. Okay, and so now this becomes equational reasoning. Okay, what about the copy rule? Okay, and alpha has to be fresh. And what do we do on the right-hand side?
P cross alpha, P and alpha. And then just P.
Okay. So because it's epsilon, we can use it. We get another copy alpha, which we can now use from then on. We can iterate this rule. We get many as copies of this as we want. Okay.
That will make the derivations correspond, but as far as the system is, you don't actually ever need to do that.
Okay, so that's a very good question. So the way that I presented the system so far, okay, I presented, I think, all the crucial rules. We get a bijection because whenever the copy rule was used, this rule was used over here. Okay, but all the rules kind of make sense. The only really weird rule is this one. From the resource perspective, I say alpha and doesn't require any resources. Okay, copy it and get a second copy of it, which is labeled by alpha. So it would be nice if we didn't have to use this rule. Okay? Because from the resource semantic perspective, it seems artificial to do this, right? Because it has not, there's no connective, right? Over here on our linear logic side, okay, it was a judgmental transition because we went from A valid to being A true, and that made perfect sense because that's how validity is defined, right? We have to be able to use these assumptions. But when we come over here and we have uniformly gammas and deltas which are labeled with resources, suddenly copying doesn't really seem to be justified. We have to do it if you want to get a bijection of the proofs. Okay, so the question is, can we get rid of that? Okay, so maybe you can say again what your idea was. Why don't we need that?
Well, I mean, like, however A at alpha is used in the subderivation, you could just use A at epsilon instead, and then the proof in FP would stay the same.
Well, I'm a little worried, for example, about if A is used at some alpha in the initial rule.
Okay. I thought we were going to change the initial rule.
Okay, how would you change it?
Like we now have A, B, and then concept, something like that, not exactly.
Okay, so let's see if we can do that. Okay, so if we, how would we have to prove bang A proves bang A, right? And we would, when we start, this would be at alpha, and we try to prove bang A at alpha, right? That's how we would start. Okay, so now, what's our first step? Bang left. If we tried bang right, it should fail, right? Because it's epsilon, and we're not at epsilon. Okay, so then we should get bang A at alpha, and A at epsilon, and we have bang A at alpha. Okay?
Because alpha will be removed from
Ah, right. This is alpha times epsilon. So this is epsilon because the left rule here removes the alpha, of course. Yes? Okay, now we're in this situation.
we are allowed to use the band right.
Now we're allowed to use the bang right rule. Okay. Okay, and now?
If you're allowed to use identity in that way, then you just be done.
Right. If you can use identity for A at epsilon proves A at epsilon, then we'll be done, right? But if you have to use in the form A at alpha proves A at alpha, then what happens here? Then we need to use copy, right? And then this becomes, we get the addition assumption A at alpha, and we get the license to use alpha, so we have A at alpha proves A at alpha, right, by using copy. Okay. So we could short circuit that proof without using copy. Hmm?
Right, never mind, yes.
Yeah.
Yeah.
Okay. So with these rules, we can now do the copy, and then we're done. But it seems odd, okay, that in this system over here, we wouldn't be able to use this assumption to prove this conclusion, that we would have to copy it first, right? It seems difficult to justify, okay. Okay, so if we do that, then the copy rule goes away, okay. Now we have to reconsider all our other rules, right, to figure out how we're going to use that. Okay.
Because all the left rules kind of change.
Right. How do they change?
Because the A tensor B could be at epsilon or something.
Right. So in particular, this case here, for example, we would have to say A at P proves A at P, right? Does that make sense? Okay. Okay, what would we do with the cut rule change?
Alpha is no longer
Okay, we'd have a cut-bang rule. What does it look like? Gamma proves A at epsilon, and then gamma A at epsilon proves C at R. Gamma proves C at R, right? Okay, so that makes sense. Now it's tempting to get rid of the alphas here and to get rid of this P here and just say, if you can prove gamma A at P, then we're allowed to assume A at P, okay, to prove C. Well, we're not quite ready for that yet, okay? Let me say A at P proves A at P. What can this P actually be here, this one? Right, alpha or epsilon. Okay. If you want to generalize and allow more complicated things there, then we need to be very careful about these assumptions that we made, that every label appears only once and all these things. We have to re-examine all of that. So we'll think about that next lecture. So for today's lecture, we'll just say the things that label the assumptions are going to be alpha or epsilon. So when the P occurs here, when we write P, we actually mean it's one of these, or equal to one of these, right? Everything's up to equality. Okay, good. So then what happens here? We don't need the copy rule. So here, how would we rewrite this?
Well, the alpha is allowed to be like an alpha or an epsilon.
Right.
The rule still kind of works because the P star Q is still going to be P.
That's right. Okay, so it could be a Q, okay, which could be an epsilon or an alpha. And we have to remove the Q, and we get the P here. Okay. How about this rule? Well, we can't change anything here. It needs to be epsilon, right? That's what bang means. This rule went away. Now we need to worry about the tensor rule. How about this one? That stays the same because there's no assumptions involved. I mean, the P star Q is split into P and Q. Okay, and what happens here now? So the alpha needs to be a Q. Okay. Anything else change in that rule? No. Seems to be okay. All right. Okay. And so we just in the soundness statement, I think the soundness statement stays the same. We just need to make sure that gamma restricted to P keeps the things that are true at epsilon. Okay. But we no longer get the bijection of the proofs. So if we make this generalization, where do we actually change the bijection? Right, so the copy rule goes away, but what that means is that we can find...
It doesn't say exactly when we copy.
Right, right. So in this resource system, we can directly use an unrestricted assumption. When we map it back, what corresponds to copying it, then using immediately the left rule for it, right? So the proofs here are in this new system, in the resource system, are somewhat, I don't know, more compact or something, because you don't have to explicitly copy the unrestricted assumptions. You can just use them directly wherever you need to use them. Okay.
Is that similar to the focusing? When we only copy when we actually need it?
Right. So there is some relation to focusing. And so what happens like I said, I'm not going to try to do this today. But what happens is if you allow focusing, then on the left-hand side you have not just alpha or epsilon, but you have arbitrary assumptions, arbitrary P star Qs and so on in the assumptions. So this is kind of a very small part of focusing, which says that when you copy, you immediately have to apply left rule to the same thing. Okay, and so that's actually it's related. I have never actually made that formal, but it's a part of what we want to do with focusing. Okay. Okay, so now we have this calculus. So one way to use this is to think about resource management again. So that's what I'm going to finish the lecture with. Okay. So because somehow resource management should have gone away with this at this point, right? Because all assumptions go to all premises, right? So what has actually happened with resource management? Yeah?
For example, in the tensor rule,
Yeah.
you still
Right, so instead of guessing it, what we're going to do is we're going to collect constraints over those resource labels, okay, and then solve these constraints, okay. And that actually has some advantages over the resource management system which we gave before, okay. So let's just rewrite the tensor right rule to get the idea, and then we'll do an example. So if you want to make that explicit, we're in gamma, and we have A tensor B, and we have some resources R. The way we would make that explicit would be gamma at turnstile A at P, gamma at turnstile B at Q, and we'd have a constraint that R equals P times Q, okay? But we wouldn't know immediately, we wouldn't try to solve this immediately, make a guess how the R is being split. We would just carry along this constraint, this equational constraint. And then as we build our proofs, we'll collect more and more constraint. When they become inconsistent, then we know we shouldn't be able to go down that path. And if we can solve them all simultaneously at the end, we know we have found a proof. Okay. So the advantage of this over the resource management system is that our resource management system that we wrote down was very specific for a left to right proof search, where we do the first sub-goal first, and then we go to there. And it kind of only worked for focusing. In this kind of a system, you can decide you can work on this for a while, then you work on this for a while. And you just need to make sure that you globally keep your set of constraints consistent so that any step that you make is still allowed. Okay. Whenever you try to make a step which would make the equations inconsistent, then you're trying to do something which doesn't have a pre-image, okay, on the linear logic side. And it would be linearly incorrect to do that. Okay. So what we're doing is we're a deterministic algorithm for moving resources around. We're replacing that with some kind of unification or equation solving as we're going through the proof. So let's try to do an example of that. To see how that kind of thing works out. Let's see. Does anybody have a theorem we should try this on? Let's see. We could try currying or something like this. So P arrow Q arrow R implies P tensor Q arrow R, right? That's part of the currying. Okay. So when we start, oh, yeah, the letters are not good. Okay, A, B, C proves A, tensor B proves C. Okay, and when we start, what do we have? I guess we would have no resources, so we do this at epsilon, right? Okay, so first thing is we make this assumption, and then we make this assumption. So now we have assumption A, arrow B, arrow C would be at alpha, and we had A tensor B at beta. And we try to prove C at alpha star beta, right? So far there isn't anything interesting going on in terms of constraints because we can just always calculate it, right? We have calculated this. This is epsilon times alpha times beta. Okay. So now how does the proof actually proceed? Right, the tensor left is invertible, so we have to apply the tensor left rule. Does that introduce any non-determinism? The tensor left rule is still over there, right? So we would have to solve the equation that the right-hand side equals something times the beta. We can solve that, right? So in the tensor left rule, the P would be equal to alpha, is that right? And the Q would be equal to the beta. So this one is kept. This one would be kept. A or B at beta. We get A at beta 1, is that right? B at beta 1. And on the right-hand side, we would have C at alpha star beta 1 star beta 2, right? And so far, we didn't really have to make any difficult constraints. We just solved them right away. Okay. So,
B at beta 1, B at beta 2.
oh, yeah, sorry. Okay. Okay, so if you try to now apply the left rule to this thing again, okay, it would have to solve the constraint that alpha times beta 1 times beta 2 equals beta. Okay. And that would fail, obviously, because the two things are, you cannot split the right-hand side in this way. Okay. So what do we want to do now? We want to do the left rule on the implication, right? Okay, unfortunately that rule is gone. So we're going to have to reconstruct that rule. Okay. So we would have to take this alpha times beta 2, and we have to equate it to alpha times p times q, right? Okay. Okay, so we can solve that because we know that this doesn't have an alpha and this doesn't have an alpha in it. So we can cancel these. And now we know beta 1 times beta 2 equals p times q. And these are new variables. So maybe I should, I'm not sure how to, maybe I just capitalize them. Okay, so we don't know what they are. We know that their product equals beta 1 times beta 2. How many possibilities are there to take beta 1 and beta 2 into p star q? There's 4, right? Each of them could be epsilon, right? So there's 4 different ways to split these two assumptions, A and B, into the two branches, right? Both could go to the left, both could go to the right. A could go to the left, B could go to the right, and B could go to the left, or A could go to the right. And so those are 4 different solutions to this equation that beta 1 times beta 2 equals p times q. And so instead of enumerating, we keep that as a constraint. So what are the premises now? I'm going to write it here. On the left-hand side, from the same set of assumptions, let me call them gamma 0. Okay. What do we have to prove? A at capital P, which is still a variable. Okay. So all of these here are called gamma 0. Okay. And what's the second premise? Yeah. B implies C. B implies C at, it's some new gamma, right? Small gamma. Proves C at, okay. And what is the thing we have to prove it at? This capital Q and the gamma, right? Okay, because the alpha we canceled, and so the rest needs to come out to beta 1 times beta 2, and it does that, okay? If this one comes out to P and this one comes out to this Q, okay? And what I wrote as small q there, I meant to say gamma. Okay, let's try to do the first one there. So we have this is gamma naught, and we're trying to prove that. Okay, we notice A at beta 1, right, from here. And so at this point we say, okay, this succeeds, and beta 1 must be equal to P in that case. So we add that to our constraint. Beta 1 equals P, okay? Are you okay on that one? Okay. Yeah?
But how should we know that that's exactly true?
Oh, we don't. Oh, we don't. There could be other proofs, right? So,
So we could
We could backtrack, find another proof. And also, we should do all this in the focus setting. In the focus setting, there'd probably be only one proof over there. Okay. But since we're not focused, there might be other proofs, so we might have to backtrack. But if we choose the identity, which we can certainly do, then it would propagate this thing over here. Over this there, what would we do over there? We have to apply the Lolly-Loft rule again, and what do we find in that case? So we want to apply to this, so we would get that gamma times some q equals gamma times some new variables q1 times q2. Does that make sense for the two subproofs? And what are the two subproofs? One would be gamma 0, B implies C at gamma proves B at, is it Q1? Okay, that would be the first premise here. And the second premise would be gamma 0, B implies C at gamma, and the conclusion C at Q2, no, delta proves C at Q times delta. Did I do that right? Should that be Q2? Yeah. Okay. All right. So now I should be able to use the initial rule over here, the identity rule over here, because there is B at beta 2 here, and that tells me that Q1 has to be equal to beta 2, right? And I can use the initial rule here, and that would tell me that Q2 would have to be epsilon, right? So because this delta has to be equal to Q times delta, I get Q2 equals epsilon. Okay, so now I should be able to work out all those things. What do I get? So Q is that, so Q is Q1, Q2, so Q should be beta 2. Okay? And so what's that telling me is that when I break this up into two subgoals, the B assumption goes into the right-hand branch, and the A assumption goes into the left-hand branch. And then when I split it the second time, nothing goes to the left-hand side, and only the
B goes to the left.
this B assumption goes to the left, and nothing goes to the right. That's the epsilon here. And then everything works out. Okay. All right. So it's a different view of resource management. What happens is you need a good algorithm for solving constraints over this domain. Okay. Now that's not actually an easy domain to work with. If you don't have any restrictions, this is called ACU unification, associative commutative with a unit. Okay. And you will get free variables like these Q's here, things that you don't know. Okay. But we don't have to deal with a fully general case. And the reason is because we know that constants will appear at most once in these things. And that changes the nature of the problem. Okay. So there's some people who have worked on these kind of unification algorithms. So I'm not sure what's actually the best sort of known algorithm for actually dealing with that. It would be an interesting thing to experiment with that. Under the restriction that linear logic imposes, what kind of algorithm can be devised for checking that these kind of constraints remain consistent? Okay. So Jason Reed did some of that in his thesis. I'm not sure that he actually identified a very crisp theorem there. Okay. Okay, so what have we learned from this exercise? So what we have done is we have taken linear logic the way we have introduced it so far, where we have persistent resources and we have linear resources, and these have to be split and treated in a special way. We have uniformly moved it over into an intuitionistic logic here, where all the assumptions are propagated monotonically to all all premises, and so this really is no longer linear in that sense. But the price that we paid is we introduced this additional part of the judgment here which tracks the resources, and these resources satisfy certain laws. So instead of reasoning about assumption the way they propagate, we have to reason equationally within this particular domain, okay, when we do our theorem proving. So we have traded linearity essentially for equational reasoning, okay. And in fact, there's, you can fairly easily come up with an implementation, and what you do is that all the atomic predicates get additional arguments, which are resources, and this additional argument is in a domain which satisfies the ACU equations, and then when you actually do the proof search, this time without respect to where you're actually in, you just have to make sure that you treat all these equations that you accumulate correctly. And Sean McLaughlin has actually built a theorem prover based on this idea. Okay, so it's possible to do it that way. Okay, but there's still a few things that are weird about this system, and in particular, the left rule for the additives was kind of weird, and we had to do some extra thing in order to deal with bang, and it's dealt with differently here than it is over here in some sense, because here we have two different judgments, and here we just use the empty resource. So it seemed to map into fairly cleanly over here. And so next time we'll see, when we introduce focusing into this, what additional things we can gain. And it turns out the gain can be considerable. Okay. And what will happen is that these assumptions are annotated in general, not just with something that's either epsilon or alpha, but can be annotated with a whole set of resources. And intuitively, A at some set of resources means that in order to get this assumption, I need all those other resources. Okay. Okay, I'll leave it at that, and we'll see what happens with that next time. Okay, and there's also an installment of the homework due on Wednesday, and I'll try to bring out a new set of additional questions for the last homework by Wednesday.